So in this lesson we're going to learn about the derivative, and we're also going to learn about shortcuts, our first shortcuts for taking the derivative. And there's nothing mystical here. We've already done this. It's just that we haven't done it with using x instead of a number. So let me show you what I mean. Let's say we have the problem, we want to get, let's say, d dx. We'll do a simple one, x squared. Let's say when x is 3. And so what we would do is we would do an infinitesimally small change in x, top and bottom. So I'm going to have, remember we're going to put x plus dx into the function, and then we're going to subtract the function. This is divided by dx. But we want this at 3, so we would put 3 here, and we would put 3 here. So to get the derived function, what we do is we just no longer require putting in a number. We simply leave this as the variable x, and what it does is it gives us a rule that computes the derivative at every value. Let me show you. First of all, let's simplify this. So I have to square this out. So when I FOIL this out, I get x squared plus 2x times dx plus dx squared. That's this. Then I subtract x squared by dx. Remember, we need to be able to divide this dx away. I see x squared minus x squared, so those subtract away. And then I have dx on this remaining term and dx on this remaining term, so I'm going to factor that out. And so when I factor it out of the two remaining terms in the numerator, I get 2x plus dx. We still have dx in the denominator. Now these divide away. So I have 2x plus dx. And remember, the derivative is real, and so I drop the dx at the end, and I get 2x. So I have d dx x squared equals 2x. Or another way this is written is d x squared dx is 2x. Both notations are acceptable. This is basically treating, this notation is treating this like a fraction, and it's putting this on the top of the fraction, so it looks like that. So the derivative of x squared with respect to x is 2x. So what does this mean? Well, this is a formula for the slope at every point on the graph of y equals x squared. So if I draw a reasonably good graph of y equals x squared, you know what this looks like. It's just standard parabola. Okay? If I draw a pretty accurate graph, and remember, if you're going to visually interpret slopes, the scales have to be the same. So I'm trying to make 1 unit up here be equal to 1 unit over. Plug in 1, I get 1. Plug in 2, I get 4, minus 1, minus 4. I'll plot a few more points that I know are on the graph. And then if I connect the dots, I get a reasonably good graph of y equals x squared. This, of course, goes on forever. It's a parabola. There's the graph of y equals x squared. So the derivative here, 2x, is a formula. It's a function of x that tells us the slope at each point along this curve. So if I choose values of x, if I choose, let's let a here, I don't want to confuse notation. So if I choose different values for x, negative 2, negative 1, 0, 1, 2, and plug them into here, I'll get negative 4, negative 2, 0, 2, 4. These are telling you the slope at each point along this curve. For example, when x is 0, the derivative of x squared at 0 is 0 according to this, and we see over here we have slope 0. The tangent line is slope 0. At 2, this tells me the slope should be 4. And if I look over right here, if I draw a line with slope 4, up 1 over 4 through this point, it indeed does look like the tangent line. Or when a is negative 1, I get d dx x squared at x equals negative 1. This says it's going to be negative 2. So if I look over here, if I draw a line with slope minus 2 down 2 over 1, I should get something that looks like the tangent line. And it does. It looks pretty good. So, what we've got here is this now is doing the derivative calculation that we did up here, but it's doing, like, instead of saying let's put in 3, let's put in 4, let's put in 2 and get lots of different answers, it's doing them all at once. It's saying, okay, let's just leave this as a variable, and now we've done the calculation, and now we don't have to keep running through this process over and over again. I know the derivative of x squared is 2x, and that means I can just plug values into this now, and this would give me the slope at any point along this curve. This is called the derived function. It's a function that's derived from this one, or more commonly this is called the derivative. So if this is x squared, the derivative of x squared is 2x. And in Newton's notation, which we learned about, Newton's notation is particularly good for summarizing things like this. We'd say if f of x is x squared, then f prime, there's the derived function of f at x, is 2x. And so this is saying if I want the slope at points along this graph, I plug values into here. So notice this, plugging numbers into here, gives you y coordinates along the curve, if we were to graph it. This gives you slopes. Now, the next thing I want to talk about, sort of part 1, you'll have practice on doing some of those. But the next thing I want to talk about is that going through the whole process of using the infinitesimals gets very long and tedious. And so we need to learn some shortcut rules for taking derivatives. Okay? And one of the first fundamental rules you learn, shortcut rules, is what's called the power rule. Okay, it's one of the most important shortcuts, and fortunately it's very, very simple. Okay? And it simply says this: if f of x is x to a constant power, this has to be constant here. So that's n represents a number, 2, 3, 4, 1/2, whatever, any number. Then f prime of x is n x to the n minus 1. So this says whatever this power, if you're starting with x to the n, to take its derivative, you bring the power down and put it in front of the x, and then you reduce the power by 1. This works for any constant value of n. It doesn't have to be an integer, it doesn't have to be a whole number, positive, negative, whatever. Okay, fractional, this works for any n. So for example, if I do x squared, like we just did, then using the power rule, the 2 comes down in front, x, and we get 2 minus 1. We reduce the power by 1. And that, of course, is just 2x to the first, which is we already got. It's 2x. We have that on the previous page. If f of x equals x to the 5th, f prime of x equals 5x to the 4th. Okay? This rule is usable in other circumstances, or it works for any constant power here. For example, if I have to do square root x, you say, well, that's not a power of x. Well, yes, it is. We know this. We know this is x to the 1/2. And this is one of the main reasons we learned about fractional powers, is so that we can use this derivative rule. Then f prime of x will be, the 1/2 will come in front, and we'll have x, and then we'll subtract 1 from this, and 1/2 minus 1 becomes negative. It's negative 1/2. This is a perfectly good answer. But if we're going to plug numbers into it, it's also good to recognize that this negative 1/2 puts the x in the denominator and turns it back into a square root. So it's also 1/2 root x. Okay, one more. What about 1/x cubed? Well, again, it's like, it doesn't look exactly like this, but we know we can write this in this form right there, because we can say that this is x to the -3. And so by the power rule, which works for any constant power up there, the -3 will come in front. We'll have x. Then we have to subtract 1 from this, and when we subtract 1 from a negative, it becomes a bigger negative, so we'll get 3x to the -4, or another way to write this would be to put it back in the denominator. So, why does this rule work? Well, I can show you a brief proof. The proof that I'm going to show you only works for positive integer powers of x. Okay, so let's say, and we'll see the proof later for other types of powers, other types of constant powers. So let's say f of x is x to the n, where n is 1, 2, 3, and is in this set. So it's a positive integer, one of these values. So if I apply my infinitesimal definition of the derivative, f prime of x is going to be, so I do x plus dx to the n. I plug x plus dx into the function, then I subtract the function, and then I divide by dx. Then I need to simplify this and then make it real. I need to somehow cancel this dx here. Now you have to think about this. You learned about the binomial theorem in pre-calculus. But even if you didn't, we can sort of puzzle out what's going to happen here. Okay? So if I think about what's going on here, this means x plus dx, x plus dx, over and over again, n times. And I would need to distribute all of these out. And this would be a huge, huge mess if I had to write it all out. But we know that one of the powers, and only one, the way we distribute all this out is we pick a term from each one. And each, so if I go x, 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 x will be one of the terms. If I take x from each one, that will be x to the n. Then, in addition, I could take dx from this one, and then x from all the others. And I could take dx from the second one, and x from all the others. I could take dx from the third one, and dx from the fourth one, and then x from all the others, and so on and so forth. So there's n different ways to take dx once and x the rest of the time, which means there would be n minus 1 times we would multiply by x. And then there'd be a lot more terms depending on, it could be a tremendous amount of terms if n is a very large number. But all of these remaining terms would have to have dx squared or higher. So what I will do is I will write this as x to the n plus n x to the n minus 1 dx plus terms with dx squared or higher. So I'm going to plug this back over here. When I do, I get x to the n plus n x to the n minus 1 dx plus terms with dx squared. Fence this off. Then I have minus x squared from here. This is all over dx. Not the best presentation I've ever done of this. Sort of ran out of space. But now, oops, this is x and x to the n. My apologies. X to the n. And something very similar happens when we did the derivative of x squared at the beginning of this. This subtracts away. Then I have terms with dx, dx, dx squared, dx cubed, so on and so forth. All the terms up here will have dx in them, so I'm going to factor the dx out. When I take dx out of the first term, I'm left with nx to the n minus 1. When I take dx out of these, I have terms with dx, or higher powers of dx. But that's all I need to know is that they have a dx, because those divide away, and then these are all infinitesimal. And so when we make it real, these infinitesimal terms will go away, because all these terms will have dx in them. And I just get nx to the n minus 1, which is what we were looking for. All right, there's one more very important shortcut. And fortunately, well, it's two bundled into one. Fortunately, they're both very straightforward. Okay. Two more shortcuts. Well, let's not say two. Let's just do more shortcuts. These are all going to be very quick, and they're going to be very, hopefully, straightforward. Okay. One, if I have a constant, I want to take its derivative. Well, if I think of the graph of a constant, I'm not going to go through the proof using the definition, because it's pretty clear. If I think of the graph of a constant, the constant functions don't change. Their graphs are horizontal and they never change. So everywhere along the graph of a constant function, the slope is 0. And so if I have a constant, its derivative is 0. Next, worth mentioning, even though it follows from the power rule, the derivative of x itself, of course, is 1. This is just dx dx, which of course is 1. Next, this is less obvious, but it follows from the definition of the derivative in a pretty straightforward fashion. If I have a constant times any functions whatever, so k here's constant again. This constant, remember, this is not a constant all by itself. This is a constant times other stuff. This constant sits there in front of the function, and then you take the derivative of the function. So it multiplies that. For your homework, I'm going to have you prove this rule using the definition. Let me show you an example of this. So if I have to take the derivative of 7x squared, all this rule is saying is that the 7 multiplying the x just sits there. And then you do your normal rule for x squared. So you do 7 times 2x, which is 14x. Or if I take the derivative of minus 3 square root x, let's call this cube root x just to be different. The minus 3 will just sit there. It's multiplying cube root x. And then I have minus 3, and this is x to the 1/3. And then using the power rule, When I take the derivative, the minus 3 sits there, and here I get 1/3 x to the negative 2/3. And then of course I could simplify this. This becomes minus 1 x to the negative 2/3. Finally, the last shortcut is derivatives go term by term. This is the way I think about it. If you want to write it in fancy notation, it's if I have multiple terms, f of x plus g of x, you do each term separately. This is not true for products if we're multiplying two things together. We'll learn about that in the next lesson. But derivatives go term by term. So what I mean here is if I have to take the derivative of a multi-term function, for example, let's say I have to take the derivative of a polynomial, 7x to the 5th minus 2x cubed plus 8x minus 4. This would be horrible, a huge amount of work to do directly from the definition. And now it's almost trivial. This here tells me we're going to go term by term. We're going to take the derivative of each term separately. Rule 3 here tells me that the constants just sit in front. So I see this 7 and this minus 2 and this 8, and they just sit there. And then I have the power rule going on each one. So I get, so the 5, I get 7 times the derivative of this is 5x to the 4th via the power rule. The 5 comes down in front, and I reduce the power by 1. The minus 2 sits in front, and then the power rule applies again. 3x squared. The 8 sits, and the derivative of x, if you recall, is just 1. And then the derivative of a constant by itself, a constant term, is 0. And so we end up with 35x to the 4th minus 6x squared plus 8. And just think about the amount of work it would take to get that result from here using the definition. These are an incredibly powerful collection of shortcuts.